All right, here we go. So this is what we're going to try until something else happens. Um, I'm going to go through some lessons with you guys from where we left off. My goal is to post 2 videos on Google Classroom every day, uh, one with the notes and then one with me going through the problems that I have assigned. Um, can't require you to do these things because not everyone has access to this. So I want you to make sure you understand that at this point, this is just if you are worried about getting behind. If you just want to, stay up on your math. If you're bored, if your parents are, getting mad at you because you're not doing anything, all those kinds of things. But nobody's grade is going to be affected by not doing this material. Um, Also, as we go through this, is a learning process for all of us. So make sure that you give me any feedback that you want, probably through Google Classroom, or you can just email me directly, and we will make adjustments as we go, as we need to, because it is an ever-changing landscape out there. Okay, so today's topic is volumes. So what we started with doing integrals was using integrals to find the area underneath a curve. Then I'm sure you will recall that we changed the game a little bit and said instead of just finding the area underneath the curve between the curve and the x-axis, we could change it and find the area between two curves by subtracting. And that is where we left off. So what we're doing with volumes is we are taking a curve and we are rotating it around the x-axis. Tomorrow we'll rotate it around the y-axis because why not? But we'll start with rotating it around the x-axis and then using calculus to find the volume of that three-dimensional figure. Okay. And so the basic idea here is really the same thing as we have been doing with area underneath the curve. For the area underneath the curve, we took rectangles, found the areas of the rectangles, added them all up, and then we talked about if you use an infinite number of rectangles, then add up all the area, then those areas will eventually be equal to the area underneath the curve. The same thing is true with volumes, except for what we are going to do is we are going to take the area of a cross-sectional piece of the shape, and if we add up more and more of these cross-sections, then eventually as we do, if we get an infinite number of cross-sections, then the volume of all of these infinitely small cross-sections will be exactly equal to the volume of the three-dimensional object. And so when we were doing the rectangles, the dx that you guys all love at the end of the integral stood for the width of the rectangle, which of course is infinitely small. In this case, the dx is going to stand for the height, basically, of the cylinders that we're going to use to come up with the volume of the object. Okay, so really that's all blah blah blah. What you need to know is here is the formula. It's a very simple formula, surprisingly simple for what we're doing being so complex. That's not very helpful. It's this little piece right here. This is showing how we're getting it. What we're doing is we're saying that the volume of a solid is going to be equal to the limit as n approaches infinity of the sum of an infinite number of the areas of the cross-sections times the height of the cross-sections. And so when we change that into an integral, this is the Riemann sum. If you take this and change it into an integral, then you get the integral from a to b of the area of the cross-sections times the heights. So what we're going to start with is we're going to start with curves that we are, like I said, rotating around the x-axis. And so if you can look at these spectacular drawings that I'm able to make with my mouse from the comfort of my own home, if I take this curve and I rotate it around the x-axis, then the cross-sections that I'm going to end up with are all circular. They're all cylinders. And so the shapes that we're going to do for the most part, we'll cover some at the end of the section in a couple days where they're not cylinders. But for the most part, all of these are going to be cylinders. So the area of this cross section is going to be the area of a circle. So we're doing circles instead of rectangles, basically. And that area is pi r squared, I'm sure you all recall. The pi is a constant, and so a lot of times what we're going to do, in fact all the times what we're going to do is when we do our integral, we're going to pull the pi out front and then just integrate this variable here. And the radius of these cylinders, which again you can see from my beautiful drawing here, is going to be the y value of this function at this point. That's going to equal the radius of the cylinder. So really what we're doing is we're just integrating. We're going to change this into, instead of being pi r squared, we're going to do that as pi y squared because the curve and the radius are the same. And then that is going to be what our integral will be. Now you all know better than to think that it's going to be that simple for all eternity. Of course, we'll make things more complicated as we go down the line, but this is the basic idea. So let's start with a super fun one, which is to show that formula that you have been told is true, which is the volume of a sphere is equal to 4/3 pi r cubed. Let's show that that is in fact the formula for the volume of a sphere using calculus. So here's our setup. So what we're going to do is we're going to take this semicircle right here, and we're going to rotate that around the x-axis. And hopefully you can kind of visualize that and see that if we do that, what we'll end up with is a three-dimensional sphere instead of this two-dimensional semicircle. The radius of the sphere we're going to say is r, and so that's why this is going from negative r to r, because that's the radius of this. We have talked about, especially when we were first learning how to do integrals, I gave you some of these to do, and so you should be a little bit maybe familiar with this formula for a semicircle, that y equals the square root of r squared minus x squared. So I think we did one where it was the square root of 4 minus x squared, and so I told you guys that's a semicircle with a radius 2, so we just found the area of the circle and then cut it in half. But here we're trying to show it for the most general case, so we're using r as a variable instead of an actual number. So this is the setup. This is the equation. This is the curve. We're going to spin this bad boy around the x-axis, and that is going to give us a sphere. All right, so in order to find the volume of that sphere, we need to first figure out what the area of a cross-section of that would be. Like I said on the previous slide, that's going to be pi y squared, because maybe it would be a little bit easier to see on this drawing here. If I were to take this and rotate it, wow, rotate that around the x-axis, woof, then I would get a little cylinder that looks like this. Okay, that is the worst thing I've ever done in my life. And the radius of that cylinder is going to be changing depending on where we are on the sphere. As I get closer here and here, the radius of the cross section is smaller than it is right here. So don't be confused when I'm talking about radius of the cross sections. I'm not talking about the radius of the sphere. I'm talking about if we draw tiny little cylinders perpendicular to the x-axis, I want the radius of those cylinders. So the area of the cross section is going to be, like I said, pi times y squared, which very conveniently in this case, if I take this and square it, the squared and the square root cancels out, and so we're left with the simple formula pi times r squared minus x squared, okay? Okay, so we're trying to find the volume then from negative r to r, because we're integrating with respect to x, we're going this way, of the cross-sectional areas. We just figured out up here that the cross section is going to be pi r squared minus x squared dx, so that's the integral that we're going to do. This might look intimidating right now, but we're going to pretty quickly get this simplified into something that's easy to do. So the first thing that we're going to do is we're going to recognize that there's some symmetry here, that the volume of, the sphere, you can take it and cut it in half. This half right here on the right, the volume would be the same as this half here on the left. So instead of going from negative r to r, we're going to go from 0 to r, so I'm just going to go from the middle out to the end, and then I'm going to double that, because there's one here on the right, and there's one here on the left. And then, like I said before, we're going to scoot the pi onto the outside of the integral sign. So now all we're trying to do is figure out the antiderivative of r squared minus x squared. Keep in mind that the real reason that we have this dx here is to tell us what our independent variable is. In this case, our independent variable is x. So the r squared is just a constant. So the antiderivative of r squared is just r squared times x. The antiderivative of r squared is not r cubed over 3, or 1/3 r cubed. That is the antiderivative of x squared, because that is our independent variable. So this antiderivative turns out to be not so bad. And then again, we are doing this from 0 to r. Okay? So 2 pi r squared x, because if I take the derivative of r squared x, the answer to that would just be r squared, minus x cubed over 3. I know we've done in class 1/3 x cubed. Hopefully you can understand that this is the same, just written in a different form. Okay, so now I need to plug r in for the two variables. So if I plug r in for the x right there, r squared times r would give me r cubed. So that's this guy right here. And then if I plug r into there, then that's of course just going to be changed from x cubed over 3 to be r cubed over 3. And then normally we would subtract from this what we get when we plug the lower limit in to our function, but if I plug 0 in for both of these x's, then everything just cancels out and we end up with 0, so nobody cares. Alright, so now we're just going to do some simple math to finish this up. R cubed minus 1/3 of an r cubed is 2/3 of an r cubed. This is where we would have lots of questions as a class about the magic that I'm doing to come up with that answer. And then if I go 2 pi times 2/3 r cubed, 2 times 2 is 4. Nothing else can happen. So my final answer is 4/3 pi r cubed, which is the formula that you've been given for the volume of a sphere since your days in geometry. So that's pretty exciting stuff. Calculus is pretty awesome. We used it to show that the vertex of a parabola was in fact negative b over 2a, and I think we used it to show that the formula that Mr. Weber always makes you use in physics for projectile motion works by taking the antiderivative of acceleration and going up from there. I don't know if you remember all that, but right on. Okay, so if that was confusing, then go ahead and re-watch that a little bit, pause it. I wish I was there to answer your questions. That was a pretty complicated thing to just kind of throw at you. I'm sure we'd have about a 10-minute discussion with on some of the finer details of that, but it is what it is. This is the world we're living in right now. Okay, so let's try another one. Let's find the volume of the solid obtained by rotating around the x-axis, the region under the curve y equals the square root of x, from 0 to 1. So here is our setup. Here's the curve y equals the square root of x. Again, we're going to take this and we are going to rotate it around the x-axis. And so the shape that we would get, if you can kind of visualize that, would be sort of like a car headlight, sort of a parabolic mirror, I don't know, half of a loaf of bread, a very deep bowl on its side. Not sure how you want to think about that. So we're going from 0 to 1. Our equation for this curve is y equals the square root of x, and so that means the radii of all of the cylinders as we rotate them around here is going to change based on where we are on this curve. but the radius of all of those cylinders will always be, the struggle is real. The radius of all of these will always be equal to the y value of the curve, which is the square root of x. So, thanks calculus. That means this is a pretty easy problem to solve. The area of the cross-section is pi y squared. That's always going to be our case when we're just rotating things around the axes. In this case, y is the square root of x, and so if I square the square root of x, the square root of the square root cancel. So all I'm doing really is finding the integral from 0 to 1 of pi x dx. No big deal. Okay, so like I did before, since the pi is a constant, I'm going to put that out there in front and just do the antiderivative of x. Antiderivative of x is super simple. It's x squared over 2, or 1/2 x squared. If I plug in 1, then I get 1/2. If I plug in 0, I get 0, and so the area of this cross-section, let's see if I could like kind of show that a little bit. The area of this cross-section, ooh yeah, that's fun. If I should have used that tool before. If I were to take and rotate that around this curve, would end up having a volume of just pi over 2. So here's a little bit maybe better graphic of what we are doing when I'm talking about taking this curve and rotating it around the x-axis. We're getting all these infinitely thin cylinders adding up all of their volumes, and then we find the volume of that is pi over 2. Okay? All right, so like I said, if we were in class, these two examples would have taken us probably half an hour. I know that's a lot to take on for you just sitting at home. So like I said, email me if you have questions, and I'll try and respond as well as I can. But I think we'll go ahead and just stop there and have you try a few of these problems on your own. Do you have to do these problems? No. What if you don't do these problems and some people do? And then when we come back to class, kids are in different places. I don't know. We'll figure it out when I see you. So just do whatever you want to do. All right, so I'm going to shut this down, and then I will make a video of me going through these problems, and then post that as well, so you can watch that, and hopefully that will help. Okay, hope you're all doing well. Bye.